In this video, we want to solve another problem with the work-kinetic energy theorem. You throw a ball up with speed v, and it reaches a height h. Using the work-kinetic energy theorem, at what fraction of the total height was the speed v over 2? This is the type of problem physics professors love to ask. They give you some situation, you're going to change something, and by what fraction does the result change? Students often have problems with these types of problems, even identifying what exactly they're trying to find. Also, understanding what's going on in the problem at all. Remember, just reading a problem doesn't mean you understand it. Sometimes it can give you a false sense of confidence. Make sure you spend some time in your visualization, drawing your picture so you really know what's going on. So let's do that and see if we can identify specifically what it means, fraction of the total height. Here's my first picture. So I have this ball, and it's going up in the air at some place. Its velocity goes to 0. I have a coordinate system where the origin here is at the place where the ball starts. There's a height h where the ball reaches, and I have positive x going up. I'm going to look at sort of a second situation here. Let's assume I sort of throw the ball again with the same velocity up. And there's some location x where the velocity is then half its initial velocity. This is the height I'm looking for, the height at which the speed is v over 2. So what does it mean, the fraction of the total height? What that phrase means exactly is x divided by h. If the final height is h, and it goes to a height x when its velocity is v over 2, that fraction of the total height is just x divided by h. So what sort of physics do I want to apply to this problem? Well, I think I want to apply the work-kinetic energy theorem, and so I've put that out there. Here's the total work is equal to the change in kinetic energy, which is the kinetic energy final minus the initial, which is 1/2 mv final squared minus 1/2 mv initial squared. I don't really know how to solve this problem yet. I don't know how to find this thing. And so I'm using some physics I think applies to the problem, and I'm going to apply it and see what comes out of it. What can I learn? The first thing I'm going to do is I'm going to apply the work-kinetic energy theorem to this first throw. So why would I do that? It's the simplest one to me. I know that the final velocity is 0, and so I'm going to apply it to the simplest problem to see what I can learn. So I'm going to do a free body diagram. There's only one force on this problem, and that's a force due to gravity. I'm going to identify the positive x to be up, so it's consistent with my other coordinate system when I want to calculate the work done by this force. I notice that this is all one dimension, and the forces are constant. The force due to gravity doesn't change. So I know that the relationship to calculate the total work then is just that net force times the displacement, where in this case the value of these numbers is the magnitude of the forces, and the sign indicates their direction. The displacement, delta x, is just positive h. It's the final position minus the initial, or if I just want to draw that vector of the displacement, it starts from the initial position and goes to the final position. And that's a vector of magnitude h, and it's pointing in the positive x direction. The force due to gravity has a magnitude of mg, and it's pointing in the negative x direction. So when I calculate the work, that's just negative mg times h. And it's equal to 1/2 mv final squared, which is 0 because the final velocity is 0, minus 1/2 mv initial squared, which is just negative 1/2 mv squared. A little bit of algebra, I divide out the minuses and the m, and I now have a relationship between the initial velocity and the final height, which is hopefully good. I don't have an answer yet. I don't even have x in any of my relationships, but I think that was a good process. It's going to help me in the future, and I have a relationship I might want to use. So now let's look at this sort of second hypothetical throw, where I'm looking at the displacement from the origin to a height x. Now in this case, the free body diagram is the same, so I can use the one I have before. The relationship between work and the force and the distance is the same, but the displacement is different. For my second throw, the displacement is just a positive x, where x is that height at where the velocity goes to v over 2. So the total work in this case is negative mg, that's the same as before, times x. That's equal to the change in kinetic energy, which is 1/2 v final squared. Now in this case, v final is v over 2, minus 1/2 v initial squared, which is just v. I want to simplify this, so I can take this 1/2 out of here. I square it, it becomes 1/4, and bring it out and multiply it by the 1/2 at the beginning, and it gives me 1/8. So I have a 1/8 mv squared minus 1/2 mv squared, and that is a negative 3/8 mv squared, because 1/2 is negative 4/8. Putting that together with the total work I calculated, I have a negative mgx is equal to negative 3/8 mv squared. Well, I can again divide out the minus signs as well as the mass from both sides. And now, look at this. Right here is this v squared, and I have a relationship for v squared from before, so I can substitute in 2gh for that. G times x is 3/8 2gh. I can divide out the g's, and then multiply the 2 and 3, and I get x is equal to 6/8 h, simplify the fraction, or 3/4 h. Now that I have a relationship this simple, it's really easy how I'm going to find x over h. I just divide both sides by h, and I have now the final answer. The fractional height, or x divided by h, is equal to 3/4. It does make some sense, because it's at least between 0 and 1, and it's certainly not half. We don't really expect it to be half because the distance is not linear in the velocity. We have this v squared term, but it's at least less than h, and so that's a good sign.